This is the first video for week 10. Here we are going to look at limit theorems. But before we do that, let's define what we mean by a function being bounded on a neighborhood of a point C. So let A be a subset of R, f a function from A to R, and let C be a cluster point of the subset A. Then we say that f is bounded in a neighborhood of C. We say that f is bounded in a neighborhood of C if we can find some delta bigger than 0, right, and a constant m bigger than 0, such that the magnitude of f of x is less or equal to m for all x in the intersection of A and a neighborhood V delta C. That is, can we find in some neighborhood V delta C of C, okay, such that if an element sits inside the intersection of A and this neighborhood, okay, then the magnitude of f of x for that x, the magnitude of f of x for that x is less or equal to m. So if that happens, then we say that f is bounded on a neighborhood of C, and that neighborhood is V delta C. So let's look at theorem 1. Let A be a subset of R and consider this function f from A to R. Now, if f has a limit at a point C, then f is bounded on some neighborhood of C, okay? So what we are saying is that if the limit as x goes to C of f of x exists, then there is some neighborhood V delta C of C on which f is bounded. Let's look at the proof. Now, assume that f has a limit at C. That is, assume that limit as x goes to C of f of x exists, and call that limit L. Then, this means the limit being L means that given n epsilon bigger than 0, you can find a delta bigger than 0 such that the distance between f of x, and L, okay, will be less than epsilon, okay, whenever will be less than epsilon, provided the distance between x and C, is less than delta. Provided the distance between x and C is less than delta. Let me say that again. So given n epsilon bigger than 0, okay, there will be a delta bigger than 0 such that the distance between f of x and L will be less than epsilon, provided the distance between x and C is less than delta. So assume that the limit as x goes to C, f of x is equal to L, and then let's fix epsilon to be equal to 1. Remember, epsilon is bigger, anything bigger than 0, so we can take epsilon to be equal to 1. So let's fix our epsilon to be equal to 1. You can fix epsilon to be equal to 2, 3, whatever you want, 0.5, so long as it's bigger than 1. There's nothing special about fixing epsilon equal to 1. We just do that for convenience. So let's fix our epsilon to be equal to 1. Then there exists a delta bigger than 0, such that the distance between f of x and L is less than epsilon, which is equal to 1. Let me say that again, okay? Given epsilon equal to 1, right? There exists a delta bigger than 0, such that the distance between f of x and L is less than epsilon. In this case, epsilon is 1. Okay, so we have that one. Clear this. So now let me clear this also. Now we have this inequality here. Okay, this is true provided the distance between x and c is less than delta. So as long as the distance between x and c is less than delta, then the distance between f of x and L will be less than 1. Now, using this inequality here, we have seen this many times in class, just applying the triangle inequality. It comes from the triangle inequality that the magnitude of f of x minus the magnitude of L is less or equal to the distance between f of x and L. So using this this inequality here, okay, we say that this inequality is true. Okay, all right. So that tells me that the difference between the magnitude of f of x and L, okay, should be less than 1. Right? So then you simply take this to the right, okay? Then you get that the magnitude of f of x will be less than 1 plus the magnitude of L. So if x belongs to this intersection here, okay, if x belongs to that intersection there, right, that means if x is in A, such that the distance between x and c is less than delta, okay, that's what this means, okay, with x not equal to c, then we have that the magnitude of f of x will be less than the magnitude of L plus 1. We get that from this inequality here, this one. Okay. Now, set M to be the maximum. If C is not in A, then simply set M to be the magnitude of L plus 1. Then you have that the magnitude of f of x, okay, will be less than M, which M is the magnitude of L plus 1. Now, if that is if x is not in A, but if that is if C is not in A, but if C is in A, remember this inequality here, f of x, the magnitude of f of x less than the magnitude of L plus 1 holds for x in A intersection the neighborhood, the delta neighborhood of C minus x equal to C. So this holds for x not equal to C, this inequality. Now, if C is in A, then you take your M to be the maximum of this one here, okay, which is this one, and then the magnitude of f of x. Then either way, you have that the magnitude of f of x is less or equal to M. So a few definitions. Let A be a subset of R. F, G, and H are prior functions defined on A. Okay. Then we define the sum function as being this one here. You take f of x plus g of x. You define the difference as being f of x minus g of x. You define the product sum as f of x times g of x. Multiple of f by b. The multiple function, okay, f times b to be b times f of x, and then the quotient function f divided by h as being simply f of x divided by h of x. Remember that we require that h of x is not equal to 0. So with these definitions, we have the following theorem. If A is a subset of R and f, g, and h are real valued functions defined on A, with h of x is different from 0, with h of x different from 0 for all x in A, and if C is a real number, which is a cluster point of A, and B is any real number, then we have the following. That the limit, if the limit of f of x as x goes to C is L, the limit as x goes to C of g of x is M, then the limit of the sum is simply the sum of the limits, and the limit of the difference is simply the difference of the limits, and then the limit of the product is simply the product of the limits, and then the limit of a constant multiple of f is just b times L if you multiply b f by b here. So the limit will be b times L, and the limit of the quotient will be the quotient of the limits, provided the limit as x goes to C of h of x, which is h, is non-zero. So let's do the proof for just one part of it, for the sum. We are going to do the proof for the first one, okay, that the limit of the sum is the sum of the limits. So let epsilon be given, epsilon bigger than 0 be given. Since this limit is L and that limit is M, we can find two constants, delta 1 and delta 2 bigger than 0, such that if x in A satisfies this inequality, okay, then the distance between f of x and L will be less than epsilon over 2. Similarly, if x in A is such that the distance between x and C is less than delta 2, then the distance between g of x and M is less than epsilon over 2. So you simply let delta be the minimum of delta 1 and delta 2. If you do that, then if x is in A, if x in A satisfies that the condition that the distance between x and C is less than delta, then you have that this one, okay, f plus g of x minus L plus g, this can be written as this, all right? Then you just combine f of x with L and g of x with M to get this, okay? Combine f of x with L and g of x with M, and then use a triangle inequality to get this one here. And then since this one is less than epsilon over 2, and this is less than epsilon over 2, so the sum will be less than epsilon over 2 plus epsilon over 2, which is equal to epsilon. And so we see that the limit as x goes to C of f plus g of x is L plus M, which is this one here, L plus M. So let's look at the Squid Theorem. It says the Squid Theorem is the one we know before from the sequences. It's similar. If f, g, and x are functions on A with this property, okay, that f of g lies between f of x and h of x for all x in A, and if the limit as x goes to C of h is L, and the limit as x goes to C of f, no, is also, yeah, is also L. If the limit as x goes to C of f is L, and the limit as x goes to C of h is also L, then the limit as x goes to C of g is also L. That's the Squid theorem. Okay? So if f, g, and h satisfy the same equality, and the limit as x goes to C of f of x is equal to the limit as x goes to C of h of x, then the limit as x goes to C of g of x must be the same as the other limit, the limit of x, the limit of f, and the limit of h. So as an example, you have this function. Let this function show that this limit is equal to 0. Okay, so we use the fact that the sign lies between -1 and 1. And so since the exponential function is an increasing function, that gives you this inequality, okay? And multiply through by x squared, because x squared is bigger than 0, you get this inequality here. Now you have that this goes to 0 and that goes to 0. So the conclusion is that this goes to 0 by the Squid theorem.